So making sure everybody is in the right spot. This is a workshop using the open source library 51. I'm going to show you guys how to go from a data set with no labels to figure out how to annotate the right images to get labels, fine tune a or not classifier, a detection model on top of that, and then run it across your entire data set and do an evaluation and kind of see how it performs. So kind of a end-to-end loop to go from a data set with no labels, doing some data curation to figure out which samples to actually label, and then finally doing the annotation. So a few housekeeping items here. This is recorded, so if you're missing anything live, it won't get lost. You'll get an email by Monday with the recording link, a link to the kind of the repo with the notebook, as well as a link to the data set on Hugging Face. There's also a blog that is accompanying this, so you can kind of follow along at your own pace as well. If you have questions, you could drop them in the chat as we go. I'll be switching between screens, between the presentation screen and the chat in Zoom. So I'll do my best to answer questions live. But if not, just be patient and I'll get your questions. I do ask that your questions just use the Q&A widget. If you look on the bottom of your screen, there should be a button with three dots that says more. If you click on that, there's a little widget there that says Q&A. If you drop your questions there, that'll help me as I'm, going through the presentation, because the chat can get chatty and I might miss something. So if you have a question, use the Q&A widget. So let's go ahead and get to it. I'm Harpreet Sahota, by the way. I work on FiftyOne. It's the open source library. It's for understanding and curating visual data sets and physical AI data sets. My job here is a hacker in residence, so I pretty much work on a lot of cool stuff. I try to push FiftyOne to its max. I try to find new ways to use FiftyOne, integrating models and data sets and building out plugins and things like that. We got a background in, originally started with math and statistics, and this is a while ago before deep learning was a thing. Worked as an actuary, biostatistician, data scientist before going into deep learning about 5 years ago at this point. So I've been doing work at developer tools companies for quite some time, and excited to be here and chat with you guys about how to curate a data set so that you can go and annotate it. So I'm curious, how do you guys actually look at your data today? I know this is easier to ask in person because you guys can raise your hand and answer, but if you want to drop in the chat how you are currently looking at your data, let me know. I'm guessing it looks something like this. Maybe you're browsing files in a folder, you don't got data or metadata, and you're not able to easily search by content. You're scrolling a file browser, opening images one at a time. Maybe you have a separate spreadsheet or README for anything you learned about the data. You're looking at your annotations kind of maybe in a text file or a spreadsheet, and you got a list of numbers for whatever annotation type is, bounding box in this case. And that's kind of how most people are looking at their data. But the thing is, nothing's here is really queryable, and you can't really carry over any insight that you gain to the next person who opens the folder. Of course, now there's an agent. We can use cursor agent or whatever agent of choice that you have. And it's still, you can ask the agent to write a script to visualize the data set, but still there's no structure place for labels, predictions, or embeddings to live. So the agent's kind of running some code here, and you're looking at the images alongside the annotations, and you might get the agent to spend some tokens and get you a visualization here, so you could see your annotations overlaid on your data. But that's still cumbersome. It's still tedious. It's not interactive, and that's kind of where FiftyOne comes in at the kind of high level. So for those of you who, well, just give me a kind of temperature check here. I'm curious who's heard of FiftyOne. If you've heard of FiftyOne, or you use 51, drop 51 in the chat. If you know, if you've not used 51, just drop 50 in the chat. So I'm curious. Uh, all right, so we got some people who are familiar with 51, who might have heard of it, and some folks that are not familiar with it. So 51 is an open source toolkit for visualizing, curating, and understanding visual data sets and model results. So it's more than just looking at an image. It's an interactive UI that's really built for data sets at scale. So you're able to filter, sort, tag, and kind of query across millions of samples all at once. So you have the labels, metadata, model predictions, all living alongside the data, and they're not kind of scattered about across separate files or tools. It's got built-in support for handling and identifying what matters when you're creating data sets, so class imbalance, mislabels, duplicates, hard examples, and you're able to do all the stuff with the 51 SDK and also in the app. So it's programmatic and visual. So anything you see in the app will map directly to the Python SDK. So you're able to, kind of have both flavors of working with 51. So here's just an example of how we're able to quickly create a dashboard to understand kind of what's in our data set. And the core concept in 51 is this idea of what's called a data set. So it's the core structure in 51. And it just is an ordered collection of what's called a sample object. And so these sample objects, they store and organize your data and its associated metadata. And so it's kind of, you can think of it as like a, visual equivalent of a data table. So each row is kind of a sample and each column is a field. So each one of these samples, I got the sample up right here. Again, this is the atomic element of a data set. So it'll have the disk path to media in the file path attribute. It's got these fields, which are attributes that are associated and attached to that sample. And this could store information like ground truth labels, model predictions, tags, different scalar values, and even embeddings. And every one of these are really dynamic, right? So you can have a dynamic schema where a field can be dynamically added, modified, or moved. And when you're adding a new field to a sample or declaring it on a data set, it's going to update the data set schema across all the samples. And then this is cool because now you can, slice, dice, filter, search, and sort a data set and then create what's called like a saved view or data set view. And so this is all backed by a lightweight, non-relational database, in this case, MongoDB. So you don't need to really know anything about MongoDB to use 51. It's just kind of built on top of that. And you can do a lot of cool things with 51. So, here's an example of a fairly complex data model. We have the samples on one side, the sample grids. We've got an embedding plot. We've got per field histograms. And all of this is living in the data set. So every one of these panels that get built out is driven by the underlying fields of that data set. And everything's interactive here. So you can click in a histogram and then the sample grid will filter to match. You can lasso a region of the embeddings plot and it'll also filter down the sample grid as well. And so nothing is like a special export or a second copy of the data. It's just the same data viewed through different lenses at once. And so this is kind of a practical difference between what we saw earlier, the old way, where we have files and folders and this kind of queryable data model. So we're going to see a lot of this in action today. So of course, there's a lot of cool things you could do with 51, but some of the bread and butter things that you could do is, query and filter. So you can construct queries in code or directly in the app's view bar. This allows you to kind of filter data sets by all the different fields that you have. You can do aggregate statistics, so calculate dataset-wide statistics, label counts, distribution, ranges, histogram values. You can have your predictions alongside your ground truth, so that way you can evaluate your model, spot mistakes. There's also robust evaluation kind of set of evaluation methods in 51. So you can evaluate classification, detection, segmentation models, all through 51 in the SDK. You can do instance level analysis. So you can, once you do this kind of evaluation, you can look for true positives, false negatives, and try to isolate model failures, and find those annotation errors and fix them. There's this complementary library that comes with 51. It's called the 51 Brain. And this allows you to compute uniqueness scores. Well, you can compute embeddings, compute visualization, compute uniqueness scores across the samples. This will help you remove near duplicates and really select kind of the most diverse samples for a training set. And with those embeddings, there's a similarity search that you can do as well. And then once you've kind of done this workflow of understanding what's in your data set, you can annotate your data right there in 51, and then fine tune and train your model in 51 as well. So we're going to see this all kind of live. Well, not live. You'll see how it played out throughout the next several slides. But continuing on with our overview of 51. So I mentioned that 51 is a data model. It's a good way for you to understand and visualize and kind of curate your data set. But there's also a robust model zoo that comes with 51. So it's a set of kind of ready to run models for detection, classification, embeddings, and it's really straightforward to just build an integration to register a custom model or a Hugging Face model as what's called a remote source zoo model. And so once you register a model, once you kind of, if you're using a zoo model or a remote source zoo model, running inference is just a simple one method call, just apply model. And it's straightforward to do. And definitely my favorite part about 51 is the plugins and panels ecosystem and framework. And plugins and panels let you customize, extend, and really tailor the 51 experience to fit your specific workflow and domain requirements. So, of course, we have the app that comes kind of standard, but rather than being locked into just what we give you, you could build on top of 51 and really match how your team works. So, of course, it's all open source and hackable. And so there's the plugins, which are just these modular packages typically written in Python, but also supports JavaScript or TypeScript, or you can combine both of those. And this allows you to add new capabilities to 51 that are specific to how you want 51 to behave. So you can introduce custom logic, integrations, and different kind of interface elements without really having to modify core 51 code. You just build on top of it. Panels, these are really interesting. They're miniature, fully featured kind of data applications that live inside the app. And you can have them render in their kind of own space within the app as well. So a plugin will give you kind of the underlying building blocks for a workflow, and then panel will give you kind of this surface area to make it visual and to kind of interact with data. And so now with this combination of plugins and panels, it goes from like a static tool that kind of just does one thing to something that could do anything that you need it to do. So it's extensible. So you can embed your own dashboards, connect external services, automate repetitive tasks, and in the enterprise version we have the 51 agent as well, so you can have an agent carry out workflows on your behalf. And some examples of plugins include this. So this is a fairly typical plugin that I like to build anytime a new model comes out, and it's a way to vibe check models. So in this case, I'm working with a model. This is Quen 3.8 Max. When it first came out, I wanted to vibe check it, so I built an integration with it and kind of just tested it out on a data set to see how well it was at visual grounding. So you can see here, like in the app, I'm just prompting it. The model's giving me an output, and then right there on the spot, I'm converting it to a 51 label, and I'm able to visually see how well that model performs. So it's a good use case of this plugin and panel kind of ecosystem. And you can even make more complex things than just like a chat panel like that. You could build a panel that could customize the annotation types. So that's what this annotation styles panel does. I could change the bounding box stylization right there in the app. Same thing with key points and segmentations. I can change the kind of way those labels are rendered in the app. So it gives me a customized kind of experience with 51. Another thing you could do is you can even build out custom panels that do like node-based workflows. So this was a panel that I built out that was inspired by the Comfy UI. So I took LightGraph and I made like a node-based workflow editor in 51. So a lot of stuff that you do in the SDK, you just add nodes into this kind of panel, connect them together, and build out workflows. Another thing you could do with 51 is actually like I took it a step further and actually integrated full-on Comfy inside of 51. So this is Comfy UI running inside 51, running right inside and operating on the sample that you have open. And you're running Comfy UI in there, doing your thing, and then the output you could save directly onto 51 as like a different sample, or even as like a group slice. And yet another integration that I built out here is with weights and biases. So you can see here I've built out a panel that integrates with weights and biases. That way you kind of get that full ML ops pipeline experience within 51. So you see here I'm just like logging some of my predictions to 51. From 51 to weights and biases, so that we can have that kind of reproducibility in our team's workflows. And so once this is done running here, you'll see we can open up the panel and it's right here in 51. We've got the weights and biases experience in 51. And we've got all our different views and all that saved, and we can recreate them as well. So it's that round trip. If you can't tell, panels and plugins are really my favorite part of 51. So I guess the question you might have is, does it work on only image data sets? Well, nope. You can actually use it on videos. So it has native support for videos baked into a data model, query engine, evaluation tools, and the visualizer, as you can see here. And so at the data level, each one of these videos is a single sample with kind of frame level data that's stored as frame attributes. And we have the same kind of sample level fields, video metadata, the different masks, key points, polylines in this case. So yes, definitely supports videos, and also has this concept of what's called a grouped data set, which is useful for multi-camera setups. So you can organize kind of synchronized streams and slices using a group data set. So it's just, just to define what a group data set is in 51, it's designed to organize and kind of maintain this relationship between related samples across multiple perspectives and camera views and data modalities. So you can have images, videos, and 3D point clouds. So the group is just that single multi-view scene. And then the slice is just the specific named stream, perspective, or modality within that group. And so you can mix and match modalities in a grouped data set as well. And of course, we're entering this age of physical AI now, and MCAP, well, ROS1, ROS2, and MCAP format data sets are becoming increasingly popular. And so we also have native support for multimodal data sets. So, the single multimodal sample can contain many concurrent data streams, camera feeds, LiDARs, point clouds, IMU readings, GPS, different coordinate frame transforms, all this stuff. And you're able to visualize, playback, and inspect them together in lockstep in 51. So for those who aren't familiar, like with MCAP data sets, there's this concept of episodes. So each sample in a multimodal data set represents an entire episode. And then we have streams that are just different, what's called MCAP channels and topics that are bound to one or more of these different viewer tiles. And then at the very bottom there, you can see a time track. And you can see that these messages carry these timestamps for log time, publish time, decode header stamps, all this stuff, which allows you to synchronize across all the streams. So 51 is able to read these MCAPs and render them, and you can visualize them. So I'm curious if if you're using or working with multimodal data, just type in MM into the chat. I'm curious how many are working with multimodal data sets. And also, if you might be interested in a workshop on using multimodal data sets, then uh, drop MMWS in the chat. Be interested to see who would want to have some learnings about that. And so importing data into FiftyOne is straightforward. So if you have a common format, if your data set's in a common format, Coco, YOLO, VOC, whatever, it's just one function call. But if your data is in like a non-standard format, it's just a matter of iterating over the files, constructing a sample, and then building a data set from them. So a few lines of just plain Python, as you can see here, and straightforward to ingest your data set into FiftyOne format. We've also have a large number of data sets, something like 200 now at this point, on our Hugging Face org. So you can see here we've got over 200 data sets on the Hugging Face hub, and these are just a couple of lines to get started and hands-on with the data set locally. And so the data set that we're using is actually on the Hugging Face hub as well. And what we're going to use for now and through this workshop is this data set called InSplad. So InSplad is just a real data set of drone photos that were taken during power line inspections. So the full data set itself has 10,000 images. They're hand labeled with dozens of different hardware categories for object detection. It's messy and kind of naturally unbalanced, and some parts show up constantly, others barely at all. And this is exactly the kind of data set that you might run into in the real world. And so I should note that this data set is, if you want to use it, it's CC BY MC 3.0, so non-commercial use. And we're kind of respecting that in this webinar, so don't take this and use it for commercial use. Here we're just kind of working with it and playing around with it. We're not going to work with this entire data set. Actually, I just kind of took this data set and just manufactured a subset. Manufactured a small enough subset that you can go home after this webinar, look through the code, and kind of get hands-on and do it yourself. So I took roughly 1,700 photos and have 0 labels, and I budget for just annotating a few hundred samples. Not many, just a few hundred, not samples, a few hundred annotations. So of course, if you were to pick the samples at random, you might waste a lot of your budget, whether it's time budget or compute budget, kind of re-annotating things that might be easy or maybe you understand well. And so this is kind of that predicament that we hope to solve in this, right? Because if you're picking images at random to sample, you're wasting your budget re-annotating things that you already understand, while the classes that you understand least might stay undercovered, right? So it's about just finding the right samples to actually annotate. So our task is going to be this. We're going to have an unlabeled data set, a subset of this InSplad data set, and we are going to train or fine-tune rather a object detection model on it. So we'll draw bounding boxes around specific hardware components in each one of these photos, and we're just going to work with a small number of classes. Right now, as of now, as we work through this, it's unlabeled, and I think this is representative of like a realistic starting point for a lot of folks out there in the industry. You have no labels. You need to quickly label something and just bootstrap some of those labels. So specifically, what we are going to work with in this workshop, or what we're going to try to detect, are 4 classes: tower ID plate, polymer insulator, glass insulator, and yoke. And so, like I mentioned, the data set is manufactured, so it's roughly balanced in the sense that there's about 217 images that contain each one of these different annotations. And so, just putting that out there, it is a manufactured kind of data set, and in the real world, you might have class imbalance and a whole bunch of issues, but the workflow that you'll see here will be general. And so let's get into this. Let's see how we can tackle this problem, right? This kind of cold start problem. Well, first, of course, we just should install 51. So all I have to do is this: pip install 51. So just like any other Python package, a one-line installation, and you're off. Once you install it, you want to go ahead and import 51, import this utility, which is load from hub, and you're going to load this data set from the Hugging Face hub. Right? And this is the exact workshop pool that I worked with while developing the content for this workshop. You'll have the exact same data set. So kind of working along with me, so to speak. Once we've downloaded the data set, well, we have to launch the 51 app, right? So you can launch the app in a Python script like so, then navigate to localhost 5151, and then it's running right there locally on your browser. And then from there, it's time to start working, right? So fine tuning is easy. It's just a few clicks in the 51 app. But the hard part, and the part that actually kind of determines how well your model is going to be and how useful it's going to be, is deciding which images from this large unlabeled pool deserve human attention. And then later, what should we fix? So it's really, we're not working with a modeling problem here, really. We're working with a data problem. And this is where you can use 51. And so kind of the loop that we're going to work with, it's essentially this. We're going to embed our images. We'll compute embeddings for our images. We'll compress them by tagging your duplicates. Then we'll visualize them, kind of using a UMAP projection. And then we'll use these embeddings and this embedding-based workflows to help us identify the right images to annotate. So once we've got our data set downloaded and we've launched the app, we can turn to the app and start looking at what it is that we have. So just quick refresher again, this is the 51 app. So this is a data set, so a collection of samples. In this case, one sample is one image, and each sample is going to have some metadata fields. And of course, for the purposes of this workshop, we have no labels. However, there is a holdout set that is part of this data set that is the workshop pool that has ground truths, but we're holding that back just to see how well our initial kind of, just as a way to judge our model performance, essentially. We have a holdout set here. And the first thing I want to do after looking at these images and getting a sense of what's in the data set is I just want to compute some embeddings. So if you're familiar with embeddings, and you know that essentially it's just a list of floating point numbers that a model produces by kind of looking at an image, and a number is kind of capturing what's in it. So it gives you a kind of semantic understanding of what's in the images. So two images that look similar end up with these vectors that sit close together in embedding space. And then two images that look really different end up being far apart in embedding space. And so this allows us to compare, cluster, and kind of search images by content rather than just by file name. And so everything from here on out, compressing, mapping, searching, needs the ability to compare these images. And it's really non-trivial to do this. I see that some of my, oh, there you go, animation did not work fully. Computing embeddings is a non-trivial thing, but in 51, it's just a couple lines of code. So we are loading a model from the 51 zoo. In this case, that model is the clip model. So clip is a good, strong embedding model to use as kind of a first go. And a lot of the work being done here is by this compute embedding call. So this will generate a vector embedding, so like a feature representation, for every sample in the data set using this clip model. And so we instantiate this model, and then we pass this into this compute embeddings method. and we're saving the resulting embeddings to this field on every sample that will be called clip embeddings. And once it's stored on the data set, then these embeddings can be directly referenced by name in downstream 51 brain tasks. So as you'll see, we're going to use these embeddings to compute similarity indexes, compute visualization, and do some other kind of math using these embeddings. Right. So the first thing I want to do is, as soon as I compute the embeddings, I want to compute similarity between every single one of my images, so then I can try to identify and find duplicate images. So this compute similarity method, what it does is it's going to index our data sets samples by similarity using those vector embeddings. So by passing this embeddings equals clip embeddings, we're going to use those pre-computed feature vectors that are stored in the data set's clip embeddings field to build a similarity index. And what we get as a result is this similarity index, this object, that gives us methods to sort samples by similarity or to even detect near duplicates. So here, I'm taking that similarity index and I'm calling the find duplicates method on it. And so this is going to query the similarity index that we built to help us find near duplicate examples across the entire data set. And so this threshold of 0.10 just specifies kind of like the maximum embedding distance threshold for two samples to be considered duplicates. So the non-duplicates set, we create these non-duplicate set. Let me rephrase that. So this non-duplicate set is going to be formed so that the pairwise distances between like this retained example is greater than that threshold. And so calling this method, we end up with a list of IDs that are identified, sample IDs that are identified as duplicates, a list of sample IDs that are identified as kind of unique or representative, and just a map of representative IDs to their nearby duplicates and the distances. So we'll end up with a map, essentially, of how similar each sample is to other samples in the data set. And so we could actually do this, like I did it in code, but in FiftyOne, you can also do it right in the app as well, at least for that find duplicate part. We create the similarity index using the SDK. Once it's built in the app, all we got to do is open up we installed the FiftyOne Brain plugin, open the find duplicates operator, and then let that run across our data set. And so every flagged image is in this, it'll create a view, a sample view of the data set, where every flagged image is going to be paired with the non-duplicate image that it's closest to. And so you can start to review these images here. You'll see that they end up being tagged, and we'll talk about tags in a second here. And in this initial exploration, you'll see that, okay, well, I've got some kind of near duplicate images that I should probably take care of, or at least flag that they're duplicates. Don't want to delete them right off the bat. We just want to tag them and note that, okay, we've identified these as duplicates. So later you can make that call yourself, whether you want to delete these images or not. But for right now, we're just kind of understanding what's in the data set and getting a sense of what's in it. And so once I've kind of done this workflow of looking at near duplicate images, next thing I want to do is actually, okay, let's see if there's any kind of structure in the data set. So I mentioned before, I have no labels, right? We have no labels. But does that mean that our pool does not have any visual structure at all? And so that's what this compute visualization will help us understand. So compute visualization is going to take these clip embeddings and it's going to map them to 2D using UMap. And then once I've got them mapped to 2D using UMap, it's just a matter of opening the embeddings panel. And now I see that there's actually some kind of structure in the data set. And I see that these kind of images that have similar visual structure tend to kind of clump together. Right? So when you open the embeddings panel and you can lasso around regions, and you can see that, okay, there seems to be some structure, right? Like polymer insulators, glass insulators, yoke clusters, they all kind of look like they might cluster close together. I think we saw, we'll see here again, that Tower ID gets its own really tight, isolated cluster here. And so it's a strong kind of example, of just how powerful these embeddings are and visualizing embeddings can be in your workflow. So we go through here, and as we're working through and as we're kind of looking at images, we should actually tag them as well, right? So as you're exploring the images, just make sure you're going through and you're tagging them, whether you want to include them as a potential kind of match. I use this generic tag of potential match for it being a decent image for us to try to use for annotation. And so this is just kind of demonstrating that tagging workflow. But what I really want to do is find images that I want to quantify just how interesting an image is, right? And so that's what this uniqueness and representative score do. So we've got the embeddings already. We've visualized them at a high level. The next thing I want to do is compute these metrics to help better understand the quality of an image, if you would. So just touching on this very quickly, this compute uniqueness is what it does under the hood. It evaluates how distinct or isolated each sample is relative to the rest of the data set. And so you'll use this kind of metric primarily during data set curation and even during active learning to kind of identify and detect outliers, find near duplicates, and help you select really a diverse set of samples so that you could bootstrap model training and bootstrap annotation and model training. And so what compute uniqueness does, it's a non-trivial workflow that is abstracted away in one function call, but it'll retrieve the pre-computed feature vectors that are stored on the sample under the clip embeddings field, and just measures the distribution and proximity of samples within that embedding space. So it's going to identify each sample's three nearest neighbors, apply a weighted distance calculation, and normalize the resulting values across the entire data set. And so the output that we get is just a scalar float field named uniqueness that's populated for every single sample. And it's normalized from 0 to 1. So higher value, meaning closer to 1, means that this sample is like isolated, highly unique. And a lower value, closer to 0, means that this sample has a lot of close neighbors. And so, potentially surfacing duplicate images. And representativeness just measures kind of how prototypical each sample is of the large clusters within the data. So it kind of helps you identify those quote unquote standard or common examples that represent the main patterns in the data set. And this is useful for really balancing and selecting representative examples for labeling. So similar to uniqueness, we're going to read the pre-computed feature vector from the clip embedding field. And by default, it's going to use this method called cluster center. And it runs a clustering algorithm over the embeddings and helps you locate these dense regions and cluster centers. And then calculate this representative score based on each sample's proximity to the cluster center. Right? So its output is going to be the scalar float field, by default called representativeness, ranging from 0 to 1. Higher value means that it's located near the centers of major clusters, so very highly representative of the data that we have. And lower value means that it's situated farther away from cluster centers. I see a question that came in here in the Q&A widget. How effective is embedding and using FiftyOne if we're trying to detect small object? I will hopefully show you that in a second. I'll touch on that in a second, but good question. Okay, so where was I? Yes. Okay. So now here, what I'm going to do is open the embeddings panel, open the clip embeddings panel, and then actually color this embeddings uh, plot by the different uniqueness or representativeness values. And then this helps me kind of identify now images that are highly unique or highly representative, right? So this is another building block that we can use to curate a data set and send for annotation. So something you could do with the embeddings plot. Of course, we have clip embeddings. So, of course, clip embeddings, if you're familiar with them, it allows you to do text to image similarity search. And so, what I'm going to do here is, of course, we could do it in the SDK, and I'm going to sort by similarity. And so, what calling sort by similarity does, it's going to query the data set's brain run that has the embeddings, and essentially will retrieve this index and allow us to query using just natural language text. So we could do it in the SDK, of course. And so what it's going to do is, the retrieve this index that we have under this brain key here, right? This brain key will have the resulting similarity index, and we can now search this using text. It's better just to demonstrate right here in the app. So what I'm going to do is open similarity search. I'm going to do natural language search over the clip embeddings. In this case, I'm going to type in glass insulator and run it and retrieve some of the images that closely match that text query. Right. So it's actually interesting that the clip model did quite well on glass insulator, and I think that's because clip has probably been trained on images that contain glass objects, and so it has a good sense of what glass looks like, right? And so this gives you a good leg up for selecting the right images to annotate. You could, of course, run the same exact type of workflow on all the other classes and kind of see how well it performs. So here, just opening up the glass insulator again. But I see that it kind of does a decent job with polymer insulator. There are some false positives in there as well. And of course, clips tends to struggle on this yoke object. And I think that's because, yoke has a lot of different meanings in the English language, and this is like a very highly specific use case of the word yoke. But this gives you a sense of, how powerful clip is, but then also at the same time, like how we can't really just rely on it. But we use it in our workflow, and we use it as a way for us to better understand what's in our data set. Another thing we could do is actually just search by image similarity. So what I could do is, as I'm going through the data set, as I'm tagging images, I can go through and I can click images and say, okay, I want to find images in my data set that are similar to this, and that image. So now here it's doing a similarity search, but rather than text-based similarity search, it's comparing images to images. So I could use this to identify more of the specific type of image that I want. So in this case, I clicked two images that contained a tower plate ID and use clip to retrieve images that are similar to that. And so this becomes useful if, maybe you want tower plate IDs, but you want them in different kind of angles or viewing perspectives, or you want them with different, particular type of background. Well, if you're able to identify and find those images, then select them. When you run the similarity index, you can retrieve ones that are most similar to what you're interested in. And just going back to the question that was in the chat here from Halil, how effective is it when trying to detect small objects? So I built out this panel called crop query, and crop query is kind of meant to handle this type of workflow. So it's meant to find images in your data set that likely contain an object and then mark where in each image it appears. So you could provide it, for example, a directory of pre-cropped images examples like the templates, which are just image files that you've already prepared. Maybe you cropped out the thing that you're looking for, and what it does is rather than comparing raw pixels, it's going to use one of the pre-trained vision models from the FiftyOne Model Zoo, and then convert that crop into a semantic embedding, like the embedding vector that we talked about, and these will be reference cropped, and then each one of these reference cropped will compute the embedding for it, and then each image in our sample will cut it into a grid of overlapping patches. Each one of those patches get embedded with that same model, and then because the patches are roughly the same scale as your reference crops, it becomes kind of a fair comparison, right? So you're asking, okay, does this local region look like my template? So not like does this whole entire image look like my template, but does this local region appear anywhere in my image, and where? So it's also computing similarity in the back end. So we're using cosine similarity between each patch and each template. And so the highest similarity that's found across all of those reference patches becomes a score. And then we overlay a heat map on top of the image where that little piece occurs. So I did it on a deliberately tough example here. I used yoke, which is probably the hardest class to find. And I didn't even do like a crop. I just, my references were whole entire images, as you can see here. So, it ends up striking a lot of false positives, but I think depending on what your domain is, and if you have your own custom embedding model, it'll work better, right? So this is just kind of just demonstrating that this type of similarity search can work on different levels of granularity. So it could help you find those smaller objects that are in your data set. So of course, everything we've done so far relied on clip, but that's not the only thing that's available to us, right? I think different models see different structure in the same pixels. So what I did was I used a different embeddings model called C-Radio V3, which I think is a very powerful model, and it's from NVIDIA. And I used C-Radio to compute embeddings, and then I also computed the representativeness and uniqueness scores. And we see right off the bat, actually, the embedding space for for radio differs from clip. The clip is a lot more structured. Like the embeddings plot for, C-Radio is a lot more structured compared to clip. Clip is kind of uniform and one large blob with a couple of islands, but we see that C-Radio gives us a better kind of structure in the data set. So we can use a different embedding model to help us understand our data set better. And of course, use this to help us triage images for downstream annotation. So here, just demonstrating the coloring by the different values of representativeness and uniqueness, and just showing how different the embedding space for C-Radio is. So of course, this type of search does help you find more of kind of what you already know what to look for, but we need to prioritize what to look for. And so for that, as you'll see in the accompanying code with this that comes with this workshop, I create a kind of blended score using the different uniqueness and representative values for clip and for C-Radio. And what I'm trying to do is now go from this large unlabeled pool to try to go to like a small high value set of images that I should go and annotate. So like I mentioned before we're just kind of looking for what we already knew what to look for, but this is different. We're going to fill in what search couldn't by blending signals across the rest of the pool into one score. So in this case, I mean, when you're doing this on your own, experiment with it and play with it. But I just took a blend between kind of a uh, even blend between the clip uniqueness, representativeness, C radio uniqueness, C radio representativeness, and created one triage score. And so now this gives me some signal as to, okay, what are the high value images that should go and curate, right? Because that's the whole point of doing what we're doing here. Not to randomly select images and randomly annotate images. We want to annotate the right images. So you'll see in the code, I'll link to it at the end here, that we're just essentially taking a equal blend of all these four signals. And so now that I've had this, right, now that I have this information populated on my data set, I'm going to create a dashboard. So this is a dashboard of the triage score. And then I'm also going to create plots, scatter plots that compare clip uniqueness versus representativeness, as well as C radio uniqueness versus representativeness. And then also look at clip representativeness versus C radio representativeness, clip uniqueness versus C radio representativeness as well. And this is also further helping me get a sense of what images to annotate. So I can look in the embeddings plot, sorry, can you look in the scatter plot here, and I can see, okay, maybe I want to start focusing on images that have, according to clip, a very high representative score, but also moderate uniqueness. And I can lasso in on the region in that actual scatter plot, filters down the samples on the sample grid, and then I could tag those or go ahead and just annotate those right in the app. And up until this point, everything I've showed you is like pieces, little steps, right? And it's leading up to actually annotating. So before we can annotate, the first thing we need to do is build out a annotation schema. And so an annotation schema, because you could do annotation right in the FiftyOne app, directly in the app. And so this annotation schema just defines the rules, fields, allowed classes, and then attributes when labeling or editing data directly in the FiftyOne app. So we initialize the schema. So we're opening a sample in the expanded view. So you can see here, open the sample in the expanded view. Hit the annotate tab and then create the schema. Then we could add the classes that we need, add in whatever hidden fields or attributes that we want to, and set up this annotation schema for us. And so this will set us up to do in-app annotation. All right, so with the annotation schema in place, the next thing to do is start annotating. And so now, finally, this is kind of like the workflow in action, right? We've done all these things separately. We've computed embeddings, computed the different metrics, computed the different scores, as well as the triage score. And now we have our dashboard that plots these metrics against each other. And I start zoning in on regions within the scatter plots and start actually just finding the right images to annotate. And so this is kind of my workflow here in the app. So of course, polymer insulators and glass insulators were quite easy to annotate because, like, I'm not trained in this field or domain. I don't know what these things are, but those were easy enough for me to do. But I found trouble identifying yolk. Like, I don't know what the yolk actually ends up looking like. So you can see that I'm kind of struggling to identify and label yolks correctly, while something like glass insulator is quite straightforward for me to do. And so yeah, this is just me, my annotation workflow. So you can see going back here, and then here I'm looking at filtering based on triage scores and the different metrics that we computed to help me find sufficiently complex and sufficiently unique and representative images for me to annotate. And as I'm going through, maybe as I'm annotating, I notice, okay, like I haven't seen many of this particular class. Let me do an image similarity search, pull up more images that look like this one, so I can kind of try to balance out my annotation so far. And so this is kind of me using all those metrics and plots that we have created to do annotation. And so this, of course, continue on for some time. I gave myself a time budget of about an hour to annotate images. And once I've annotated images, I'm ready to fine tune a model. So by the end of this process, as you'll see here, I'm opening a histogram, and I'm going to just show you the distribution of the different labels that I got. So I ended up annotating a lot of yoke because that part looked different in every images. Even looking at the ground truth data set, like yoke was had the most visual variety. So I figured I'd try to annotate as many yoke as possible. And then annotating the easier things a bit less. So I had a grand total of about 370 images that I annotated, and as you can see here, I think it was something like if we add all this up, I had about 600 annotations total. So not a lot after about an hour, but enough to see if I could fine tune a detector on it. So right there in the app, we have this is a plugin, and the plugin allows us to take any Hugging Face model that's part of the auto model class and fine tune it. In this case, I used the RF Detter model. By default, it assumes 3 epochs and this small learning rate. But of course, this model, this RF Detter model, it's pre-trained on 91 COCO classes, and so fine-tuning it on these 4 means that I need to reinitialize the detection head from scratch, and so I need more signal to that. So I bump up the learning rate, and you'll see this in the code example. I bump up the learning rate to 5e to -5, and then bumped up the epochs a lot more because that's what matters a lot when you're training a Detter family model. So Detter being detection transformer. So this detection transformer is going to match each image's box to only a handful of query slots using this method called Hungarian matching. And so the real gradient signal is quite sparse, right? And so the model needs hundreds to a couple thousands of steps to converge. So by default, if you use the default configuration, you only get like 60 steps at 3 epochs. So I bumped up the number of epochs. I did 75 epochs at a batch size of 16, gave me roughly 1,300 steps. And this was kind of as a first attempt. And so trained this locally. I've got a DGX Spark. It took quite quick to train on that. I think less than 25 minutes to train. And fine tune that model. And once it's fine tuned, then it's time to kind of spot check it. And so quite easy to take a Hugging Face auto model and use it in FiftyOne. So what I've done is I took the subset of images that I have not yet annotated, right? Because I only annotated something like 370 images out of the whatever 1,700 images. And so I took a view. So where I'm doing this first step here, I'm taking a view of all the not yet annotated images, instantiating the model from the checkpoint where I saved it, and then applying that model across the images that I have not yet annotated. So in this point, I've got trying to bootstrap labels is essentially what I'm doing here. And here was the results. So this checkpoint has only seen what we've annotated. And now I'm looking at how well the model is doing. And surprisingly, for the little time investment that I put into actually labeling data, I noticed that the model does quite well. It's surprisingly well for the little bit of annotation that I've done. And that's because as I'm going through and looking through all of my images, I'm trying to identify the quote unquote best images. So images that have good metrics in terms of representativeness and uniqueness. And as I'm kind of going through all of the classes here, comparing the ground truth to the human annotations, I see that, yeah, the model does a fairly good job of actually, identifying those classes that we're interested in. And so now what you can do at this point is, like I mentioned, we have no ground truth on those samples that don't have annotations. But you could still scroll through and see what it is that the model predicted, and then edit that right in the app, and then either add in those annotations, adjust those annotations, and rerun this process until you're satisfied with how good your model is performing. And then once you've got your model, maybe you've iterated on it a couple of times, you've done this loop where you've annotated, trained, quickly spot checked and evaluated. Now you've got it to a place where it's good. You could evaluate it now using FiftyOne on the held out labels. And so here I'm running FiftyOne's evaluation routine on the holdout set. So the holdout set was 100 images. And I'm just taking a look at how well the model performed. So I've got the evaluation panel. The evaluation panel is also interactive. You can see I've got the metric performance, per class performance, and then also the confusion matrix. And I can click in onto the box in the confusion matrix, and it'll filter down to those actual samples that were in that matrix. And I can look at the class, just examining again the class results. So we see that the tower plate ID was the best performing one, followed by the polymer insulator and glass insulator. And of course, yoke struggled, and that probably has to do more with me not knowing what exactly the yoke looks like, or what it's supposed to be, than the actual data curation or model itself. But yeah, the yoke was hardest everywhere. And, we saw this earlier as you kind of explored using the clip embeddings that, it didn't do that well. Even with the crop query, it wasn't able to detect yoke as well. So this indication that, okay, yoke is something that needs to be annotated a bit more and looked at more closely. And this is kind of like the core insight I wanted to leave you with here is that, the property that makes a class hard to find is the same property that makes it hard to learn from when you have a small labeled subset. And so we're doing this evaluation and we're noticing where we're failing. So that means I can go back right there in the app and fix what needs to be fixed. Of course, everything we did today runs on open source FiftyOne. If you're running this kind of on a recurring basis rather than just one, well, FiftyOne Enterprise has this pretty cool beta feature called agentic labeling. So, it'll help you with this tedious task of drawing everything by hand and automatically kind of agentically label it for you. So if you're interested in learning more about FiftyOne Enterprise, definitely check out the FiftyOne docs, type in agentic labeling, and that'll take you to the docs about this and how you can learn more about FiftyOne Enterprise. So just a recap for today's session. So we started with an unlabeled pool, a cold start, right? And then from there, every step kind of compounded on the step before it. We used search to identify potentially easy wins. The embeddings exposed what search couldn't see. We came up with some a triage score that blended different metrics into a single score so we can prioritize which images to queue. And we weren't annotating randomly, and we're annotating where it counted the most. Then we evaluated the results, and it was a confirmation that, okay, like, yeah, we actually did quite well annotating because we picked the right images to annotate. We saw that the same classes that were easy to find early on were the same classes that a model was able to learn from. And so it's really not a one-way pipeline, right? It's a loop. So evaluation shouldn't close this process. It's like it feeds the next iteration. And so now we know that when we come back to this, we see that we have low performance on yoke. We know we need to go and focus on that more and find more images to annotate. So all the code for what we've done today, I know I've shown some code on screen here. This is actually available at this repo. So the whole loop: compress, map, search, prioritize, annotate, fine-tune, review, evaluate, all that stuff. If you want to run it on your own, visit this GitHub repo. I'll drop a link to the repo shortly here into the chat. You'll also get an email that will have a link to this repo. There's a blog that accompanies this workshop, hot off the press. If you want to check that blog out for more details, then go ahead and scan that QR code. I'll drop it into the chat as well in a second. So you can go ahead and read that blog as you're going along with the code. I've got the data set here on a Hugging Face space. So you can go ahead and play around with that if you like, without installing FiftyOne or doing anything. If you just kind of want to get your hands on it, get a feel for how this works, you're able to do that in a Hugging Face space. Of course, I'll drop a link to that as well, and you'll get a link to that in the recap email. But yeah, you can get hands-on and play around with FiftyOne and play around with the crop query and the fine-tuning and essentially recreate everything that we've done today on your own. If this seems interesting to you, if you feel like you want to go deeper into FiftyOne, I encourage you to book a workshop with me. If you are in an enterprise or in a research lab and you think that your team can benefit from FiftyOne, I'm happy to come and do a workshop with you where we can either look at a proxy data set or maybe look at one of your own data sets, ingest it into FiftyOne, and kind of show you how to use it to solve your problems. So if that seems interesting, please do scan this QR code and book a workshop. We'll be happy to do that. So voxel51.com/workshops. I'll drop a link to all that as well. And if you want to connect with me, please do connect. My preferred way to connect is on X. So hit me up on X and kind of keep up to date on what it is that I am shipping in FiftyOne.